Hello and welcome back with Mrs. Stribble. Today we're going to be talking about sample spaces and how that relates to compound events. A sample space is a list or a set of possible outcomes when we have one or more things or events that are happening or occurring. There are several different ways to find or create a sample space. We can simply use a list format where we write down all of the possible outcomes. We can use a table, keeping in mind that a table will only work when we have two different events. So for example, I'm picking out a shirt and picking out a pair of pants. So two events, one shirt, one pair of pants. A tree diagram is used when we have more than two events, or possibly you can use it with two events as well. A tree diagram is specifically designed if we have more than two events. If I have to pick out a shirt, a pair of pants, and on top of that I have to pick out what jacket I want to wear. So there's three different events or choices that would recreate my outfit. We would use a tree diagram to represent all of our possible outfits in that example. So let's try an example here. How many different sandwiches are possible using the following menu options? So we're going to some sort of deli, okay? And we have two options of what kind of bread we want, wheat or sourdough. And then we have four different types of actual sandwich sandwiches. So we could have a ham, turkey, steak, or chicken sandwich. Okay. When we're creating a table to represent the number of outcomes for both of these events to happen, we take a look at each individual event. So our first event here is picking out what type of bread we want. And we notice there are two different types of bread. We have wheat or sourdough. So when we're creating the table, our first event will be represented right here. Okay, so we have wheat or sourdough. Each choice will get its own section. And then the type of bread, that's our second event. That'll be represented along here. Ham, turkey, steak, or chicken. Okay. Now the way the table works is kind of like a multiplication chart. If you remember filling out one of those, we take the one option from the first event and the one option from the second event and combine them together. So, oops, and I wrote bread when it's wheat. That's hilarious. Okay. We're talking about wheat bread specifically. Sorry about that. All right. So again, we're taking the one option from the first event and the one option from the second event and combining them, in this case, into one type of sandwich. So our first type of sandwich would be having a wheat bread ham sandwich. Okay. Another type would be a wheat bread turkey sandwich, and we would just continue filling this out. Okay, so this box right here would represent our sourdough turkey. Okay, and we just keep going. So I'm going to keep filling this out. Remember, at any time, if I'm going too fast, please feel free to pause the video if you think I'm just going too slow and hey, you've got it all down, you can fast forward the video too. Okay, almost, not the most, there you go, time-friendly thing, but it works. All right, so now that we have our table filled out, okay, again, the table represents all of our different options here. And we go back to the original question. It's asking us how many different sandwiches. So in that case, we can pretty much be done here as long as we have a clear understanding that each one of these represents one different type of sandwich that can happen. So we have 1, 2, 3, 4, 5, 6, 7, 8 different types of sandwiches. So the answer here of how many would be 8. Okay? If they asked what they are, that's where the actual sample space, that list, comes in. And we would literally have to write down all of them. Wheat, ham, wheat, turkey, and so on and so forth until we got them all down. Okay? That's how you create a table for sample space. Here's what a tree diagram would look like in this case. Again, we have 2 events. The first event is our bread. The second event is our meat. Okay? So for our first event, we could pick wheat, make sure you leave some space here, or sourdough. Okay? So now we're listing the options for event 1, or for the first event, straight on down. Okay? For the second event, each first event gives us a choice, it provides us a route to a second option or a second event choice. Okay? So if I picked wheat bread, I could pick ham, I could pick turkey, and notice how every arrow is starting at wheat, and then we go directly to that choice of meat. Steak, or we could even pick chicken. Okay? And this is kind of why a tree diagram is called a tree diagram. After you've gotten 2 or more events here, you start to get a branching out effect going on. Okay? And kind of those branches represent a tree. So hence tree diagram. All right, let's go ahead and finish this tree diagram here. So with sourdough, we do the same thing. We can choose ham, turkey, and yes, these take some time. Steak, or chicken. Okay. Now again, to answer the question, how many different types of sandwiches? Well, our last choice represents the different number of different types of sandwiches. So we go to our last choice, which was right here, our last event, and we're going to calculate or count how many pathways were created to get there. So in this case, it was 1, 2, 3, 4, 5, 6, 7, 8. We're counting up those arrows. That's all we're doing. So our answer is 8, still 8. And again, that sample space is just a list of all of them. So if it asked us what they are, we have to write down the list. Okay? All right. Let's do another example here. in this example, we need to find the total number of outcomes when we roll a number cube, that's also known as a die, and flip a coin. So again, two things happening independent of each other. Okay, first I'm going to roll a number cube, then I'm also going to flip a coin. One does not affect what's going to happen with the other. So that's why we call it independent. So the number cube is what's first. A number cube has 6 numbers, 1, 2, 3, 4, 5, and 6. Okay, so each of those numbers will go in the top section here. And then flipping a fair coin only has 2 outcomes. We could flip heads or tails. All right. Again, creating this table like we would a multiplication table. Okay. One outcome from each event goes inside each box. So this box would represent heads 1, or rolling a 1 and then flipping heads. You could say head H1, or you could say 1H. Okay. This box right here would be the 1 tails. I'm going to put the numbers first because that's technically our first event. Honestly, it really doesn't matter because you're just labeling inside what is already on the outside of your table. Okay. That's not heads here. And then 4 tails, that's a 3. 5 tails, 6 tails, 6 heads, and 5 heads right here. Okay. So again, from this table, we can count how many there are. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes when we roll a dice and flip a coin. 12 different things can happen. Okay. How would this look in a tree diagram? Well, we're still using that first and second event, writing vertically up and down here. I'm going to move them over. So our first event is that number cube, correct? Okay, so we're going to roll that number cube. And I'm having a feeling we're going to need more room here, so we're going to erase this right here. Rolling that number cube, we got 1, 2, 3, 4, 5, or 6. Okay. Our second event, flipping that coin. So we might want to put like a little notation. Hey, this is the coin, this is the number cube or the die. Okay, so that we remember. So our second choice, if we roll a 1, we could still flip a heads or we could flip a tails. If we roll a 2, we could flip a heads or we could flip a tails on that coin. If we roll a 3 on that number cube, same thing, heads or tails. It doesn't matter which one. One of them is going to happen. We know that. Okay. And just keep on going with that pattern here until we've reached that final one. There. Okay. So again, we see that for each number, we have 2 possible heads or tails with that coin. We can count the little branches to represent how many different outcomes total there are. And we see there's 2, 4, 6, 8, 10, 12. Okay, 12 of them. Now, let's say we had a third event. Okay, so over here I have a little question. What happens to these tree diagrams if we have 3 events? I told you tree diagrams were specifically made for this reason. Here's what they would look like. So let's add in another coin. Okay, so after I roll the number cube, after I flip this coin, I'm going to flip another coin. Now how many different possible outcomes could I have happen? Well, if I roll a 1 and flip a heads on that first coin, I could flip another heads, or I could flip a tails. If I flipped a tails on that first coin, I could still flip a heads or a tails on that second coin. So this is my second coin, right? So again, each choice leads to my possible outcomes for the third or the next choice, rather. Heads, tails. And again, super time consuming. Hopefully you're getting the idea here though. It's more tedious work than anything, really, if you think about it. That third choice, or that third event, I'm either going to get a heads or tails. So I have to apply that option to every other possible scenario that I already created. I feel like I'm drawing happy trees. Bob Ross, anybody? All right. And there we go. Woohoo! Now, once again, to figure out how many different options there are now, or how many different situations we now have, now that we added another coin to the situation, we would take the outermost branch or leaf, so these would be considered our leaves here, and we take the outermost section of our branches, which in this case would be the purple ones, and we're going to count them up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay? So we added one more coin to the mix, and now instead of 12 options, there are 24 different possible combinations of rolling a number cube, flipping a coin, and then flipping another coin. Tree diagram. All right, you think you got it? Well, let's see what we can do from this. So let's say we have a closet, and I'm terrible at drawing, so give me a little bit here. We have a little closet guy. And in this closet, we have some hangers. There we go. Pretty. And each the little hanger guy is holding a t-shirt for us. Okay. Now what I'm going to say is we don't have to do a tree diagram. We don't have to do a table in order to figure out how many different possibilities there's going to be in a multi-event situation, or what we call a compound event. Okay, and here's why. Gotta love that beauty of math, right? Okay, more than one way here. So here's another route to figure this out. Okay, so I got my little closet. It has 5 different t-shirts in it. And we need to know how many different outfits we can make from 5 t-shirts, 4 pairs of jeans, and 3 pairs of shoes. Okay? Rather than, like I said, rather than drawing a tree diagram, we can use something called the fundamental counting principle. Yeah, I know, kind of funny. Fundamental counting principle. And here's what this guy says. It says to find the total number of possible outcomes in a series of events, that's kind of what we're dealing with here, all we have to do is multiply the number of how many outcomes each event has together. Okay, so let me run through that again. Multiply the number of outcomes possible for each event. So going back to our closet, we have 5 shirts, 4 jeans, and 3 shoes. The fundamental counting principle says to simply take 5 times 4 times 3. 5 times 4 is 20, times 3. We have a total of 60 possible different outfits. Now, if you want to go ahead and draw that tree diagram, go for it. Be my guest. But the whole point of the fundamental counting principle was to prevent all that tedious work, because after we did so many of them, we found this pattern. Okay. So in this video, we spoke about sample space, the different types of sample space that can be created. How you can use them to figure out all your possibilities and how many possibilities there are. How we can use the fundamental counting principle to make our lives easier when dealing with multi-event situations, and how to use that knowledge of possible outcomes in multi-event situations to find compound probability.